Morning, everyone. Welcome to our third week of distance learning. I hope you guys are keeping safe. So, for most of you seniors, it's only a few more weeks. We're pretty much high school is totally over. For the juniors, well, I guess we're going to be hearing from each other until June. Anyway, for this week, we're actually going to talk about factorials and permutations and combinations. So we're going to learn when can we use permutations and combinations as a way to count efficiently particular scenarios. But before we go there, let's first go over the PGCPS, distance learning safety, right? So we'll always see this protocol posted for every video that I put up. So anyways, please be reminded that the PGCPS administrative procedures regarding appropriate use of technology, social media, and email continue to apply to our online instruction. In addition, this session may not be recorded without the instructor's consent. So because this video is already pre-recorded, obviously, this statement will not apply to us, but rather it is to be interpreted as that this recorded video cannot be distributed without my consent. So if you feel that you have a friend who could actually use the video to further their understanding about permutations or combinations or factorials, you may do so, but please seek permission from me first. You let me know that you would like to share it with them, so of course I can give you permission to do so. Anyways, a description of the applicable procedures is provided online in the Student Rights and Responsibilities Handbook. Thank you for your cooperation. As what I've been saying for the last two sessions, the Student Handbook is always available through the PGCPS portal or through the Google Classroom. I believe I've already posted up a link on the Google Classroom to take you direct to the student handbook, but you should actually scroll all the way down, as I believe I put it up there at the beginning of the school year. Right? So now that we are done with this online safety, we can now actually begin our lesson. So our lesson is about factorials and permutations and combinations. Okay, so last class, we actually introduced factorials, what it is, what it does, and how is it a convenient way of showing how to calculate a particular scenario or how to count a number of ways for a particular scenario. This week, we're going to expand on such knowledge, and we are going to incorporate that with permutations and combinations. Factorials is a important procedure in understanding how to compute for permutations and combinations. Okay, so before we go to the actual lesson, let's go over to the objectives for this week. So for this week, students are expected to solve expressions involving factorials. Number two, different permutations from differentiate permutations from combinations in counting. They are definitely different from each other. There are scenarios wherein you are required to use permutations and scenarios wherein you are required to use combinations. And finally, to solve basic counting problems involving permutations and combinations. Right, so these three would be the main objectives that we're going to try and accomplish this week. Right, so let's go on with the lesson. First, a quick review on factorials. So n factorial, read as n factorial, is an operator wherein n being a counting number, right? N factorial denotes that you have to multiply n with every counting number between n and 1. So if you have, let's say, 10 factorial, so to compute for 10 factorial, we simply have to multiply 10 with 9, with 8, with 7, and so on and so forth until we get to 1. Thus, 10 factorial is simply 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I will not go over to the exact answer with that, as that is a big number for me to do mentally, but that is the process of computing for a factorial. Right? Okay, so here are some factorial properties for us to look at. Now, these factorial properties may make our calculations easier, especially if we do not have the technology necessary to compute for a factorial. Okay, so n factorial is also equal to n times n minus 1 factorial. So this one might seem a bit hard to understand, but if we look at the example, it could be made easier. For example, let's say we're computing for 7 factorial. Now, according to factorial property number 1, 7 factorial can be expressed as 7 times 6 factorial. Now, take note, 7 factorial, when computed, is 7 times 6 times 5 times 4 times 3 times 2 times 1. This one, 7 times 6 factorial, so that's 7 times the 6 factorial. So 6 factorial is simply 6 times 5 times 4 times 3 times 2 times 1. So 7 factorial is definitely the same as 7 times 6 factorial because they have all the same factors. Right? Now notice, this property can actually be expanded, right, by doing several iterations of such a property. For example, 7 factorial can also be computed as 7 times 6 times 5 times 4 factorial. So this process, right, is a result of continuous iterations of the first property. Later, you will understand why this property is very important, especially in simplifying factorial calculations. So other properties, 1 factorial is equal to 1, which makes a lot of sense because there's only one number in this in this part wherein you have to multiply. So it's just 1. Okay. This one is the more intriguing part, 0 factorial. So 0 factorial is defined to be 1. I think the definition here is more of to support any calculations they had for factorials, because later you will encounter scenarios wherein the factorial, all right, when you're doing permutations or combinations, you will encounter a particular problem wherein there would be a 0 factorial in the denominator. 0 not being a natural count, not being a counting number, therefore could not be taken the factorial. But because of some scenarios that involve computing for a 0 factorial, thus 0 factorial was defined to be 1, just to make sure that the calculations would still work. Okay, so please remember these 3 properties. The second one, very easy to remember. It's just the first and the last one, which would be quite critical to remember. Of course, with technology, you can go straight and compute for factorials. All right, let's go over some certain examples on how we can calculate factorials. Right, so here we have 3 examples wherein we're going to solve them. Okay, and these expressions do make use of factorial symbols. So the first one, we have 3 factorial times 4 factorial. The second one, we have 6 factorial divided by 3 factorial. And the third one, we have 10 factorial all over 4 factorial times 6 factorial. Right, so if you would like to answer this on your own, you may do so. You may pause the video if you need more time and then unpause it later when you're ready to actually check your answers. All right. I think that should be enough time for you to pause the video, try to compute those by yourselves, and then unpause it to just check your solutions. All right, let's now go check them. First, we have 3 factorial times 4 factorial. Now, 3 factorial is simply 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. So 3 factorial times 4 factorial is 6 times 24. Right? And 6 times 24 is simply 144. Now take note, when you are multiplying or dividing with factorials, you do the factorials first before you multiply. So if you're given 3 factorial times 4 factorial, you don't multiply 3 and 4 first before you take the factorial. You do the factorial first. The only time that you actually multiply before you take the factorial first is if there was a parenthesis. For example, parenthesis, 3 times 4, close parenthesis, then factorial. In that case, you multiply 3 and 4 first before you take the factorial. All right. So next problem, number 2, we have 6 factorial divided by 3 factorial. To do this, of course, we can just put it in the calculator. It should give us 120. Or if you'd like to do it manually, you can compute for 6 factorial first. That is 720. And then you compute for 3 factorial next, which is simply 6. And then later, you divide 720 by 6. That is 120. Right. Now, another way of doing this, right, if you don't have technology available to you, and you are asked to compute for the exact value, right, you can do so by trying to simplify first particular expressions. Now notice, 6 factorial can be expanded into 6 times 5 times 4 times 3 factorial, following the first property of factorials we mentioned earlier. Now, you might ask, why did I stop with 3 factorial? I stopped with 3 factorial because there's actually a 3 factorial at the denominator. This 3 factorial and that 3 factorial, of course, will cancel each other out, leaving us with only 6 times 5 times 4. Okay, now that we only have 3 numbers to multiply, I think that definitely makes our multiplication problem much easier. So 6 times 5, that's 30. 30 times 4, that is 120, which is the same answer we got if we had computed for it directly. All right, so remember this technique of trying to simplify factorials first if you could not calculate for it because you don't have technology available. Right, now another example, number 3, we have 10 factorial divided by 4 factorial times 6 factorial. Right? With technology, of course, you can just do this straightforward, but you have to be very careful because take note that 4 factorial is the one being multiplied to 6 factorial. So if you made a mistype, if you mistype this on a calculator or something, you might come up with a wrong answer. So you need to be very careful with how you put in the values when you're using technology. Okay, now to make things easier for us, of course, we're going to try and simplify this and see what the total comes out to. So 10 factorial can be broken down or can be expanded into 10 times 9 times 8 times 7 times 6 factorial. You might ask, why did I stop at 6 factorial and not at 4 factorial? Well, I stopped at 6 factorial because 6 factorial is the larger factorial number, right? And canceling out a larger factorial number is much more convenient as opposed to canceling a smaller factorial number. Right? That is the reason why I chose to stop at 6 factorial. You may, of course, choose to expand this all the way to 4 factorial, but the cancellations would be a bit more tedious. Not too much, but definitely a little more. Anyways, now that I stop at 6 factorial, the 6 factorial can cancel the 6 factorial at the denominator, leaving us with 10 times 9 times 8 times 7 divided by 4 factorial. Now to continue, I'm going to expand 4 factorial. So 4 factorial is 4 times 3 times 2 times 1. Now from over here, I am going to try and cancel out some terms so that I'll be multiplying fewer terms. Now take note, times 1 or divide by 1 actually does nothing, so you don't need to consider that too much. You can just throw it away. If you'd like to cover it, that's fine. Go cover it. So we're only concerned with the 4, the 3, and the 2 in the denominator. Take note that 4 times 2 is actually 8. That means if we cancel out 4 and 2, we can cancel out 8 along with that. That removes 8. So pretty much in the numerator, you'll have only 10, 9, and 7 left. And at your denominator, you only have 3 left because 4 and 2 disappeared. As I mentioned earlier, 1 is not important as it does nothing for the multiplication or the division. All right, now note that 9 and 3 can actually be canceled with each other. If you cancel 9 and 3, it should give one more factor for 9, which is 3, because 9 is 3 times 3. Thus, canceling 9 and 3 together gives you an extra 3 on the numerator. And the 3 denominator disappears. Thus, the only numbers you have left for this particular expression is 10 times 3, which was 9 earlier, and then times 7. Right? And then 10 times 3 times 7 is simply 10 times 3, that's 30, times 7, that's 210. And the answer, therefore, for number 3 should be 210. So if you're using technology, you might need to practice of how to enter this. Maybe you could try and practice now or so, just to make sure that later, when you get into the main exercise questions, you'll be able to compute them faster and accurately. Now we go to permutations and combinations. So permutations and combinations are definitely a result of fundamental principle of counting. The only difference is that there are certain scenarios wherein permutations and combinations work, and it actually makes the expression of the answers simpler. Okay? But before you actually go with permutations and combinations, you have to make sure that you know when they are applicable. So the first condition is there should be no repetition of chosen objects, right? So once an object is chosen, it cannot be repeated. So for problems like determine how many numbers are there from 1,000 to 5,000, right? This cannot be used because digits, if you're actually choosing digits, then those digits could be repeated. Thus, it violates the first requirement for being able to use permutations and combinations because there would be repetition of particular objects. Next question. Next condition. The chosen objects need to be chosen together. So when you choose particular objects, all right, you need to actually pick them all together. They cannot be mutually exclusive. You pick the first digit, the second digit has to be also included. You pick the first person, the second person has to be included. In short, the number of ways that the objects are chosen need to be multiplied with each other, not added together. Of course, this only works for a particular case because the main guideline is the fundamental principle of counting. Probably the lesson next week I'll probably go over this when I go through the whole counting principle. So everything will be there. Fundamental principle of counting, special permutations and combinations, so that you can actually see how it works. Now, when do you use permutations and when do you use combinations? Permutations are used when it requires a particular order or position. So when you are asked to actually choose a particular number of people from a particular group, if it matters how they were chosen, like electing officers. So when you're electing officers, who gets elected as president matters as who gets elected as vice president. If you interchange the two people, right? So first case, you have person A being elected as president and person B being elected as vice president, and then you interchange their positions. Second case, you have person B being elected as president and person A, the vice president. These are two different cases, right? So in this particular case, permutations is important because who gets to be chosen as president matters. The position is important. Combinations, on the other hand, only require you to choose a particular number of objects or a particular number of people. So for example, if you're supposed to choose group members, right? It doesn't matter which group member was chosen first. As long as every, as long as the people in the particular group are the same. For example, let's say in group 1, you have persons A, B, and C present. So it doesn't matter whether the teacher chose person B first before A or C. Doesn't matter if it's person C, as long as the group is made up of people A, B, and C, right? This is how permutations and combinations differ. Permutations require a particular arrangement or a particular order is important. Combinations, on the other hand, only require the set of people or objects chosen. Doesn't matter which was chosen first. All right. Let's look at some examples here and try to see, whether we could identify which ones are permutations and which ones are combinations. Okay, so here we go. So we have examples here of 4 different scenarios, and we are to identify whether a particular scenario is a permutation or it's a combination. So number 1, determine the number of ways the president, vice president, secretary, and treasurer can be elected from a club of 20 members. So for number 1, right, would that be a permutation or a combination? What about number 2? Determine the number of ways 8 people can be chosen as members of the board from 100 shareholders. Is that a permutation or a combination? Number 3, determine the number of ways 4 people can be arranged in a line from a group of 10 students. So not only are you supposed to choose 4 people out of 10, you need to arrange them in a line. All right, so is that a permutation or a combination? And number 4, we have the number of ways 5 shirts will be packed for a trip from a closet having 12 shirts. So for number 4, let's say you're going on a trip. You imagine that you might only need 5 shirts. And so you ask yourself, okay, how many ways can I pack 5 shirts from 12 shirts? Okay, so if you would like to actually try to answer this on your own and then see the answers later, you may pause the video and then collect your thoughts and then unpause it and then see the solution later. Now remember, I'm only asking whether the following situations are permutations or combinations. I'm not asking you to give me the number of ways. We will actually do that later. Right, so if you're ready to pause the video. Okay. I think that's enough time for you guys to pause and unpause the video, whether if you try to answer it by yourselves. Right? Let's go over the answers for these particular problems. Okay. All right. So in this particular situations, numbers 1 and 3 are permutations. Based from my example earlier, election of officers is definitely a permutation, because whoever gets elected as president definitely matters, right? And so is whoever gets vice president. If you interchange the two positions, it's a definitely different outcome as the one earlier. Number 3, it's also a permutations. We have a giveaway word here. The giveaway word is arranged. So let's say from a group of 10 people, A, B, C, D, E, F, G, H, I, J. So those are the 10 people we have. Let's say you choose A, B, C, and D to form a line. Now, one line or one possible line that you can actually have is when A comes first, followed by B, followed by C, and finally D. However, if you interchange the position of B and C, then that would be a different line. As in the second line, B is actually third in position and C is the second in position. So thus, number 3 is also a permutation because the way you're going to pick them and arrange them matters. Numbers 2 and 4 are combinations. Okay, so why are they combinations? Now remember, combinations do not require a particular arrangement, order, or position for the chosen people or objects. So for number 2, we're supposed to select 8 members of the board. So in this case, it doesn't matter which person was chosen to be a board member, as long as we get the same 8 people to be our board member. Now, if the problem says out of the 8 people, they will have to choose a chairman of the board, then that is, of course, a different particular problem. Because if there is a chairman of the board, then there is, of course, importance in that particular position. But if there is no particular position here which is significant enough, then we can assume that the members, the chosen 8 members, to become members of the board does not matter on which order they were chosen. As long as those were the same 8 people chosen to become the members of the board. Number 4, determine the number of ways the 5 shirts will be packed for a trip from a closet having 12 shirts. So if a person is going to pack 5 shirts out of 12, it doesn't matter which shirt gets picked first and gets packed first, as long as it's the same set of 5 shirts that the person picks. For example, if there are 12 shirts, that's A all the way to L, if I'm not mistaken. A, B, C, D, E, F, G, H, I, J, K, L. Sir Trocino is very good with the alphabet. So let's say the person picks t-shirts A to E. So that's A, B, C, D, and E. So it doesn't matter whether I pick A first, followed by E, followed by D, followed by B, and finally C. It doesn't matter whether I chose C first, because at the end of the day, those are the 5 shirts that I actually packed for the trip. This is what combinations is about. It doesn't matter how you pick them, as long as those are the objects that you pick. Right. Okay. So if you have any questions about this, remember we do have a weekly Google Docs post. You can definitely post your questions there so that we can answer them. Right? If you don't have, there's nothing else, we're going to go over to the next part wherein we're going to compute for the actual number. Right. So now we're going to, right, we're now going to use permutations and combinations to count. Okay. All right. So the number of permutations of R objects from a total of n objects is given by the formula P permutation n R. There are other notations here. I prefer the notation n, then followed by capital P, then R. But this one I think is the most common notation, and this is what I'm going to use. Anyways, n here refers to the total number of objects you can choose from. R would be the number of objects that you would like to choose and arrange. Okay? So if you are going to choose R objects, which you are going to arrange later, or which you need to choose in a particular order from n total objects, the number of ways this can be done is given with the formula n factorial divided by n minus r factorial. Take note, in this particular case, because there is a parenthesis before the factorial, you will have to take the difference first before you take the factorial. Okay? But if you have technology and you are able to find permutations, then that should be good. Okay, so, but if not, then you can always go with this calculation. Next, the number of combinations of R objects from a total of n objects is given by the formula C n taken R is equal to n factorial divided by n minus R quantity factorial over R factorial. So take note, for combinations, you actually have an extra denominator, which is the R factorial. Take note, pretty much same fraction or so, except that for combinations, you have an extra denominator here in the presence of R factorial. Now, because combinations has an extra denominator, obviously, combinations will always have a fewer number than permutations, right? It's like if you divide 10 by 2, dividing 10 by 2 twice actually gives you a smaller number because you have more denominators. You're dividing it more times as opposed to only dividing it one time. Right? Now, what is the significance of this R factorial? R factorial actually is the number of ways that you can arrange R objects. For example, if I ask you to arrange 5 people in a line, that would simply be just 5 factorial, right? Because the first choice is 5, the second choice is 4, the next is 3, the fourth is 2, and then finally you have one choice left because there is only one person left. Thus, it's 5 factorial, right? So if you have R objects and you need to arrange them all in a line, that is, of course, R factorial ways. The procedure for taking combinations is you are taking out the number of ways that those R objects can be arranged, and thus it makes it fewer. Whereas for permutations, those arrangements are important. So you see there is no division here of R factorial. Okay, so that is a very, very important thing to remember. If you want to arrange R objects, you want to arrange all of them, they can simply be done through R factorial. However, I would like to express my reservation about having identical elements. We will actually go with that on our next class. Right, so let's try to see this permutations and combinations in action based from 2 of our examples. Oh, I'm sorry, before we actually go to the examples, we'll connect them. So as I mentioned earlier, fundamental principle of counting is still the parent of permutations and combinations. So even if you forget how to use permutations and combinations, as long as you understand fundamental principle of counting, then it should be no problem. The only important thing to remember is that the number of ways to arrange our objects is our factorial ways. That is the only important thing to remember. And for combinations, it is important because it does not matter how they get picked, or it's not supposed to be arranged, right? Okay, so in the example later, when I solve it, I will solve it through two ways. One, using permutations and combinations. The other, using just plain fundamental principle of counting. All right, so these two examples are pretty familiar, as we definitely saw them in the previous example. Right, so for the first one, we're supposed to elect 4 officers from a club of 20 members. And for number 2, we're supposed to determine the number of ways that 8 members of the board can be chosen from a group of 100 shareholders. Right, so if you would like to solve this on your own, you may pause the video, work it on your own, and then unpause it, and then watch for the answers and solution later. All right, I think we're now ready for the answers and the solution. So let's get on with it. All right, so as I mentioned, all right, the fundamental principle of counting is like the parent technique. So regardless of whether you forgot how to use permutations or combinations, you can still solve the problem using plain fundamental principle of counting. Right, so number 1 is of course a permutation problem, while number 2 is a combination problem. So we should be seeing permutation approach for number 1, while we should see a combination approach for number 2. Right, so for number 1, because it's a permutation, I'm going to use a permutation technique. So take note, there are 20 members in the club, and we're supposed to select 4 officers from them. Now, since the position is important, we definitely know that this is going to be a permutation. So thus, we set it up. P20 taken R. P20 taken 4. So that is simply 20 factorial divided by 20 minus 4 factorial. Take note, the denominator here is the difference of the two numbers here. Then you take the factorial. So you don't put here 4 factorial, you put here the difference between 20 and 4, which is 16. That is the number you are going to take the factorial of. So P20 taken 4. Okay, if we expand our factorial so that we can cancel the 16 factorial at the bottom, we see that everything here comes to about 116,280. So there is 116,280 ways to elect 4 officers out of those 20 members. Now, as I mentioned, we're going to connect that with fundamental principle of counting. Right? So since there are 4 officers, then we need 4 possible positions. All right, which of course represents the position for which officer is going to be there. So let's say the first position is for the president. So which is usually the first one elected during an election. So since there is no officers selected yet, there is 20 possible people who can be elected as president. Right? Thus, the first position has 20 choices. The next position will only have 19. Why? Because one person has already been elected as the president. So therefore, this president cannot also be selected as a vice president. And this is very, very important because, as I mentioned, permutations requires you not to have repetitions. right? So there's 19 people left to be chosen as vice president. Then after you've chosen a president and a vice president, you're going to elect a secretary, which only gives you about 18 people to choose from, right? And then finally, once you've chosen also a secretary, that brings you to the last position, which is the treasurer. That only gives you 17 more people to choose from. So if you multiply 20 times 19 times 18 to 17, we are sure that's also going to give you 116,280. Because if you look here closely, notice the 16 factorial cancels out and you actually have the same numerator left to multiply with this one, right? So as I mentioned, even if you forget how to use permutations and combinations, as long as you remember how to use fundamental principle of counting, you should be fine. All right, now let's go to number 2, wherein this one is a combination. All right, so for number 2, all right, we need to choose 8 board members out of 100 shareholders. So since they're only board members, it doesn't matter which board member was chosen first, as long as we choose the same 8 people who would be the board members. So we now have a combination approach. So C, 100 taken 8. So that would be 100 factorial divided by 100 minus 8, then factorial. So 100 minus 8 is 92. All right, so remember, take the difference first before you take the factorial. Then finally, we have an extra denominator of 8 factorial. All right, so here we go. So this one should be repeated as an extra denominator over here. Okay, so now we're going to simplify this. Okay, so what we're going to do is we're going to expand the 100 factorial here, stopping when we get to 92 factorial. I'm stopping at 92 factorial because 92 factorial is the bigger factorial between the two denominators. Allows me to cancel that one out, right? So once I cancel 92 factorial from both numerator and denominator, I am now left with 100 times decreasing, counting numbers all the way to 93, divided by 8 factorial. Of course, I'm going to expand 8 factorial here. I did not write down the cancellations for each one, but of course, you may write down how they cancel each other out. So after I canceled some stuff here, eventually I computed that to be 186 billion with a B, 87,894,300. So that is the number of ways you can choose 8 board members out of 100 shareholders. Right? Okay. So now let's go over how to compute for that using fundamental principle of counting. So the same approach, we're going to choose 8 board members. So we can do that by choosing first the 8 people. So the first person, the first board member, we have 100 possible choices. The next board member, we only have 99 because we've already chosen one for the first board member, although the position is not important. What's important is there's 99 people left to choose from for the second board member. And this goes all the way up to 93. Right? Now, the problem with this one is that this one considers how they were chosen. And since this is a combination, it does not matter how they were chosen, then whatever this product is has to be divided by 8 factorial. Because 8 factorial refers to the number of ways these 8 board members could be arranged, whether in terms of being picked as a board member, or if you think of it as a line, the first person picked being the first person in the line, and so on. So if we divide this one by 8 factorial, we actually get the same expression we had here earlier. That being the case, we also should expect the same answer, which is 186 billion with a B, 87,894,300 ways. Right? So hopefully you learned something for this week, preferably how to use permutations and combinations properly. All right. So I hope that you guys keep safe. And if you have more questions, remember to always use the weekly Google Docs to post in your questions. That way, when I address those questions, it will actually be viewable for others who might have similar questions, or if they haven't realized, they would actually like to ask the same question. Right? So thank you. Be safe and bye.